Okay, so now let's see some of the applications of the first law of thermodynamics as applied to the ideal gases. Now, in these set of applications, what we'll be doing is we'll be taking some of these external variables as constant. So sometimes we'll be taking the volume constant, the temperature constant, or the heat constants, and things like that. So before we start that, let's look at a very general case of Cp minus Cv as applied to the ideal gases. Now, in the previous video, we saw how Cp minus Cv was calculated to be this equation, right? The equation number 17. So this is the equation that we calculated. There were no assumptions in here about the ideal nature of the gas and things like that. So this is Cp minus Cv for any system. Now, when we apply this for ideal gases, what happens? Now let's see. Okay. Now, our first point that we are trying to see is what is going to happen with this term. So this is del E by del V at constant temperature. Like if you have the temperature constant, what is the change in the internal energy when you have change in the volume? Okay, so to understand what happens here, let's come and look into one of the very famous experiments that was done. So in here, we have the Joules free expansion experiment. What is the meaning of free expansion? The meaning of free expansion is like if you have, let's see that example in here. So let's say you have a container A and a container B. There is some gas under pressure which is compressed in container A. There is a valve and that till now this passage connects container A to B, but this valve is the one that is stopping this gas to come out of container A. Now this is immersed in a water bath and we are trying to measure the temperature of the water bath. Now what happens when this gas under pressure is the valve is released in here. So the gas from here starts to travel in B. So this was evacuated, okay? So there was a free expansion. There was no work done in here. So like there was, since this is evacuated, that means that the pressure applied was 0. Therefore, the PV, the pressure work, the work term PV becomes 0, right? Now, if there is a change in temperature in the gas, that means that there has been change in some kind of like internal energy, okay? But when the experiment was done, it was seen that there is no change in temperature as observed by this thermometer, okay? So it was noted that there was no change of temperature when air is allowed to expand in such a manner as there is no work done. So in this case, there was no work done. So when there was no work done while this gas was flowing from the pressurized container A to the evacuated container B, there was no change in temperature, okay? So this was the Joules free expansion. Now, when I said that the PV was 0, so that means, now let's write down the first law. So dE is equal to, we know what that is, del Q minus del W. Now what we see is this is 0. Why? Work becomes 0 because the PV becomes 0. So this whole thing becomes 0, right? So work in here is 0. So this term is cancelled. Now what we have is dE and dQ. Now what we can write in here is the change in temperature in here observed was also 0. So the change in temperature was 0, therefore dQ was also 0. So according to the first law, if you have work as 0 and dQ as 0, you must have dE, which is the change in internal energy, also 0, okay? Now we know that dE, as we have seen before in a previous video, that this can be written as del E by at constant temperature plus del E by del T at, this should be del V. Okay, now we know that there was no change in temperature. So dT itself becomes 0. Okay? Now, we see that there was an expansion of the gas, right? So the gas had some amount of volume in here, and the gas expanded when it moved to B. So dV is a positive number. It is a non-zero number. But we know that dE is 0. Why? Because W and Q both are 0. So this should be a 0. This dE should be 0. So we know that this should be 0. This is 0. dV is a non-negative, is a positive number, is a non-zero number. That means that this term, so how do we make this dE 0? This is taken care of. This is a positive number. So if we make this del E by del VT as 0, then only we can make the dE 0 as required. Okay? That means this term is 0. Okay? Getting this term 0, and we name this equation, we number this equation as equation 18. Okay? So this is only true for an ideal gas. Okay? So this thing was only true if the gas in the Joule's free expansion experiment was an ideal gas. So Joule and Kelvin both, they did this experiment and then came up with the conclusion that this is true only when the gas inside these countries, the gas used in this Joule's free expansion experiment is an ideal gas. Now, from for our perspective in here, from now on, whenever we say that a gas is ideal, we are referring to the property of that gas represented by this equation. So whenever there is an ideal gas, when we have a free expansion of that gas, this equation should hold true. Okay? Only then that gas can be called an ideal gas. Okay? All right, so this is equation 18. Now moving on to finding out our value of Cp minus Cv. Now, what did we find there? That dE by del Vt, this term is a 0 for an ideal gas. Okay, so this is true for an ideal gas. Okay, so in here, this term cancels out. Okay, this term becomes 0. What do we get outside this? Cp minus Cv, simple, this term, del V del T P times P. Now, our job is to find out what happens for the gas in here. Okay? Now, we remember that for an ideal gas, PV is equal to nRT. Okay? Now, if we want to find out the value of this equation, we have to find out the value of V. How do we find out the value of V? So V is nRT by P, right? So how do we write this value in here? So the value in this purple box. So let's try and find out the value in this purple box. Okay, so we want to find out del V by del T P. We know the value of V, which is here. Okay. Now, R and T, N, R, and T being constant comes out of the equation, and this becomes N, R, and T, and, sorry, the T is, this is a constant P, so this is at constant pressure, right? So pressure comes outside, and this whole thing becomes del T by del T at constant pressure, right? So this whole thing is 1, right? This whole thing becomes 1. So essentially this del V by del Tp becomes nR by P. So everything in that purple box is nR over P. Now let's then use this equation. So let's substitute this purple box with this purple number. So this becomes nR over P times P. Now pressure and pressure is cancelled out and we are left with nR. Okay? Now this is the value of Cp minus Cv. Okay? Now N is the number of moles of the gas that is being used, and R is the universal gas constant, 8.314. So you can also write this as 8.314 times N Joule per Kelvin per mole. Okay? Now this becomes equation 19. So now we know how Cp minus Cv for an ideal gas is N times R.